Right, let's start with this first question. How many nuclei were in the rock to start with? We know that originally 0.04% of 210 grams of unobtainium 131. Let's start with the 131. That tells us that 131 grams would contain 6 times 10 to the 23. Let's go down here. Okay. So 131 grams would contain 6 times 10 to the 23 nuclei. We don't have that amount. We have 0.04% of 210 grams. Which is 8.4, 0.084 grams. So to get the number of nuclei in there, I need to do 6 times 10 to the 23, divide it by 131, and then multiply it by 0.084. And that's 3.85 times 10 to the 20 nuclei. That's the first one. How many are in the rock now? Well, we're going to get that from the activity. Using A equals lambda n, I can work out n is going to be A over lambda. The half-life is 3 billion years, so let's work out lambda from that. Lambda is going to be ln2 over 3 billion years. Make sure you put that into seconds. So it's ln2 divided by 3 times 10 to the 9 divided by 365, 24, and 3600. Which is 7.33 times 10 to the minus 18 per second. So I do the activity 2136 divided by 7.33 times 10 to the minus 18. And that is 2.92 times 10, sorry, 2.92 times 10 to the 20. How old is the rock? Right, okay, so now we're basically using this equation, n equals n0 e to the minus lambda t. Although I'd rather just get it in terms of half-lives, so I'm going to just do it a bit differently. I'm going to work out the fraction that's decayed. So I'm going to do 2.92 divided by 3.85. Don't know why I keep doing that. 2.92 divided by 3.85. So that's 0.75, 0.76. And that's a half to the power n, where n is the number of half-lives. And I can work out n by doing ln 0.76 divided by ln 2, I think. Let's just work that one out. So I get a negative number, but it's the same thing. So I get, that's roughly 3.99 half-lives. No, sorry. 0.399 half-lives. So I can work out the time because it's just 0.4 times 3 billion, which is 1.2 billion.